Okay. So in any case, we go back historically, memory used to be really, really, really expensive. So we look at some of our technologies. Really, when the idea of our modern computer was being, when we came up with it, we were operating with the framework that memory is about is a problem that we have to fix, right? That's something we need to really consider when we do stuff, and that's where working with different how we store information and working with different bases really became helpful for us to represent stuff inside of a computer, right? Because we needed to think about footprints and stuff like that. All right, so and that's where we see some of those leftovers from older programming languages. Like, so in C, C++ came from C, so it has the same primitive types. Java came from C++, it has the same primitive types. C# came from C, well, came from Java, whatever, so it has the same primitive types. So these primitive types are still around today. How many of you have ever used a short in a program? Most of us haven't, or if we did, it was for no good reason, right? You didn't have a, or were you running out of memory on your laptop? Okay, so you still do that. Okay, so when you're doing C or C++ stuff, all right, but generally speaking, you're not going to see people using shorts today. Yeah. Each character is used by 1 byte, right? 1 byte, yeah. 1 byte. But in the older days, SMS without multiplication, it does not have all the 56, right? It will have less than 128. So they can use just 7 bits. Sure. Yeah, they didn't represent the entire ASCII character set. Yeah. So they use only 7 bits. The extra bit, they shift from the next character. Yeah. So for every 8 bytes, they will say like 1 byte. They save a byte. Yeah, I got you.
Now, if you're using longs or something, you're doing a lot of algorithms with longs versus shorts. Wouldn't it be faster to use shorts, or does that not matter?
It really doesn't matter, because where these things get stored, like when you store a 16-bit value, you're storing it into a 16-bit memory register.
Okay.
A 32-bit value gets stored in a 32-bit memory register, and we're going to say all memory registers are the same speed. There might be some difference there, because we go back to the previous slide a couple slides ago, whenever we said it. Where did I say it? I said it somewhere. Hierarchy memory, yeah. Closer to the CPU the memory is. So, technically one register might be a little bit closer to the CPU than another. So at that point you're talking about the distance of a, something that's in millimeter, or micrometers. So you might have slight different performance differences, but generally speaking, we're going to think of hardware registers as all being the same speed.
Okay.
Fast, super fast. Now, having said that, when we start getting down to the assembly level, though, when we are talking directly to the CPU, certain things might get converted into shorts or bytes or things like that if the assembler is able to notice that you didn't store a value that was larger than a certain size in it. That has to do with how quality of compilers or something. Generally, though, as a programmer who's working in a high-level language, we're going to use ints most of the time. If an int isn't big enough, we'll put it in a long. If that's not big enough, then we got to go and look at what object types are in that language. So like in Java, we have big integers and stuff like that, which stores arbitrary size numbers at the cost of speed. The bigger the number is, the cost of speed and also memory footprint. You'll basically never see a modern high-level programmer use a short. We're talking super rare. You will still see bytes. Why do you think you still see bytes? That would be a bit, a single 0 or 1. Why do you think we still have people operating with bytes? Yeah, but even then, our characters in our modern programming languages are Unicode based. So they're 16-bit values. 65,536 characters instead of 256. So, but we do a lot of video streaming, right? And when we're dealing with video streaming, things typically arrive 1 byte at a time. Whether it's serial or parallel streaming, you're still getting things in bite-sized chunks. You're not really trying to be memory efficient. It's just the right size box for the problem. Make sense? So at that point, it's more a right tool for the job than even caring about memory. Just fits. It just fits how things are being passed. Okay. So now let's talk about some number conversion stuff. So let's look at binary to decimal. Use this as my number size. So let's say we have 10111. So let's say this is our binary number, 10111, and we want to convert that into base 10 to decimal. Now, is this a legal decimal number? Could that be a decimal number? Yeah, like 10,111, right? So I had to tell you that this guy was a binary number, a base 2 number. So if we talk about bases, binary numbers, that's base 2, right? What's the legal alphabet for binary numbers? 0 and 1. We can think of this as 0 to the base minus 1. So base 2, 0 to 2 minus 1, which is 1. What about octal? Octal is what base? Base 8. All right, what's the alphabet for octal? 0 to 7. So 0, 1, 2, 3, 4, 5, 6, 7. Is that 0 to the base minus 1? Base is 8. 8 minus 1 is 7. 0 to 7. All right. Then we have decimal. What base is decimal? Base 10. That's our number system, right? Why do we like base 10? Just tradition? Great grandparents decided they were just going to use base 10 because it's fun?
Easier.
Why is it easier?
Just add zeros.
10 fingers, 10 toes? When you're a kid, don't you count with your fingers? Base 10 made sense for us. If we only had 4 fingers, we'd probably use base 8. Okay, so decimal, this is 0 through 9. What about hexadecimal? That's base 16. What's the alphabet for hexadecimal? 0 to 9, A to F. What about base 37? Yeah, just because we don't have a fancy name for it doesn't mean it doesn't exist. Base 37 will exist. Oh, base 36, sorry. So this is 0 to 9, and then A to Z. Right? Okay, so what if we wanted to represent base 37? Or base 40? So if I want to represent base 40, I need 0 through 9, then A through Z, and then I need another 4 unique single characters, right? So maybe I switch over to, I guess I could move in just the Unicode character set after numbers or something like that and just keep working down the line so that you can, you have 526 after you use your 10 things for numbers. You just use all sorts of different characters from different languages. I mentioned the joke I made earlier was, one thing you might say, well, if you need more characters, why don't you use a different alphabet? Maybe you use Klingon. Well, we looked it up. Klingon only has 22 characters in the alphabet. Now, the funny thing is that for those of you who knew what Klingon was, the show Star Trek has an alien race in it called Klingons. And, you know, in the TV show, they speak a language called Klingon. It's a made-up language, right? Some nerds have created Klingon. You search online, you can find the entire language just documented.
You lowercase and uppercase?
You could use lowercase and uppercase. Typically, those are they're used so interchangeably that you wouldn't say start with lowercase and then uppercase, because you might see people representing hexadecimal with either one. So it's probably a little dangerous to say, well, it's going to be lowercase then followed by uppercase. You'd want to probably move over to emojis or something like that. But at the end of the day, it needs to be documented somewhere. So at the very least, you know where the pattern is. Because what we're going to see here is the pattern is going to be the same. Okay? So these are our different, so we'll just say some other symbols, if you wanted to go to larger bases. And we'll talk about why we might want to do that here in a few minutes. So if we're thinking binary to decimal, something like this. We have 10111. Is our binary number, and we want to convert this guy to decimal. Here, we're going to make these buttons pretty for Sheikah. We're going to color code them. I usually wouldn't do this, but I want to make sure you think it's aesthetically pleasing. All right, so that's the ones place, the twos place, the fours place, the eights place, the 16s place. If we want to look at this a little bit different way, let's see, this will probably be green, right? This is the 2 to the 0th place, 2 to the 1s, 2 to the 2, 2 to the 3, 2 to the 4. So 2 to the 0th power is a 1. 2 to the first power is a 2. 2 to the second power is a 4. So on and so forth. Okay? So then when you convert this binary number to decimal, you multiply the top number, the bit that is in that position, times the place and add it to the next pair. So this will be 1 times 1 plus 1 times 2 plus 1 times 4 plus 0 times 8 plus 1 times 16. And that is the number 23. So you add all that up, you get the decimal number 23. Make sense? Steal this slide. Let's say we want to do octal to decimal. Is this a legal octal number? Yeah, sure. Is that only use things between 0 and 7? It's not using all the things between 0 and 7, but it certainly uses values between 0 and 7. So this could be an octal number. You see how I have to tell you what kind of value it is? I mean, we know for a fact that this isn't a base 1 number. Is there something other than just zeros? If we have letters, we know it's not a base 10 number or less. It's got to be something with some letters in it. All right, so this is the 2 to the 1, this is the 8 to the 0's place, the 8 to the 1's place, the 8 to the 2's place, the 8 to the 3's place, the 8 to the 4's place. Or this is the 1's place, the 8's place, the 64's place, what is this, 256? 256 place, then 4096? 2048. And this is the 2048th place. So that is 1 times 1 plus 1 times 8 plus 1 times 64 plus 0 times 256 plus 1 times 2048. $64 times 8 is 512. Yeah, it is. So this is not the 256 place. This is the 512 place. Doesn't change your output. So the so this is 2121. Oh, because it's okay. Yeah. 4096. 512 times 8 is 496. My other number 2048 was times 8. So this is 4096. So 4,169. Right, so 10111 in octal is equal to 4,169 in base 10. Make sense? Okay.
You can't get every number from that though. Correct.
What do you mean every number for that?
Like you couldn't represent 10 with that, could you?
You want to represent the decimal, like what's the decimal 10 in octal?
Yeah.
Yeah, you could. You would have an 8 here. So you'd have a 1 here and a 2 here.
Oh, because you can put
yeah.
other than 1.
So 12.
Gotcha. Okay.
Or it wouldn't actually be 12. That's a decimal number, but 1, 2 octal is equal to 10 decimal.
So if you have different bases, then you can also change your characters to 1 through 7.
Yeah. So this was just kind of
okay.
Here, let's give a more realistic answer for a thing for octal. So now for octal, I can change this because this could be 7, 2, 0, 5, 4. So that's using a little bit more of the octal alphabet, right? So this is going to be 4 times 1 plus 5 times 8 plus 0 times 64 plus 2 times 512 plus 7 times 4096. So just for completeness, let's just write that. So 4 times 1 plus 5 times 8 plus, we don't need the 0 times 64, because that'll be 0. 2 times 512 plus 7 times 4096. Copy all that, throw that here. 29,740. Make sense?
Mm-hmm.
Okay, so just a little practice. I'm going to give you another number here. We'll cut off one of the, make it a little bit more palatable. So let's do a 6. We'll do a 3. We'll do a 1. 1. All right, so take a couple minutes. We'll pause this here. All right, so this one. This is 1 times 1 plus 1 times 8 plus 3 times 64 plus 6 times 512. So that's 3,273. All right, everybody got that value? All right, ready for a trick? I'm gonna throw a trick at you. So let's steal this one again. So 9477. Convert that from decimal to decimal and show your work. Show your work. So this guy is the make sure we color code this again. We don't want to get on Chica's bad side. All right, so this is the ones place, the tens place, the hundreds place, and the thousands place. So this is 7 times 1 plus 7 times 10 plus 4 times 100 plus 9 times 1,000. 9477, 9477. Make sense? Okay. Hex to decimal. So I'll pick my favorite hexadecimal number. Favorite hexadecimal number is BAD. This is the ones place, the 16s place. Should be 256, right? Yep, 256. This is the 256 place. But now we need to do a little mapping here because a B is actually an 11. An A is actually a 10. A D is actually a 13. Because when we're doing number conversions, we need to have a single character representing each place. So a 10, we have to represent a different way. So we represent 10 through 36 with A through Z. Or if we're dealing with hexadecimal, you have A through F. So 10 through 15 is A through F. So that's an 11, that's a 10, that's a 13. So this guy is going to be 13 times 1 plus 10 times 16 plus 11 times 256, and that equals 2989. That's the right number, right?
Yeah.
It is my favorite hexadecimal number, so I typically use that as my conversion. I didn't just do the math in my head. I'm too old for that. It's terrible. Don't get old. Okay. So, makes sense how we can go from any base to decimal. Similarly, if I want to say we can go from base, I don't want to go too far down the alphabet. We can go base 20 to decimal. So just to keep the numbers easy here. So base 20, a B, A, and D are still going to be an 11, a 10, and a 13. But what's going to change here is this is the ones place, this is the 20s place, this is the 400s place. Right? So this is 13 times 1 plus 10 times 20 plus 11 times 400. That's 4613. Make sense? All right, so identical pattern, no matter what we're converting, what base we're converting into decimal, even decimal to decimal. Right, there aren't these special cases. And so at this point in time, nobody should ever say, oh, well, I can convert binary to decimal, but I don't know how to do the rest of them. Make sense? Pretty common thing for people to get hung up on. Now let's go the other direction. I want to go from decimal to one of these bases. So let's say that I want to convert the decimal number don't know, let's do a 63 decimal to binary. All right, so to convert a decimal number into another base, what we do is we use, how many of you remember long division? Okay, long division, so here we have that like in third grade, right? So if you have a number like 5 divided by 3, so we call this integer division, like we were talking about earlier. Okay, so you were running into integer division issues on the homework. So integer division is the same thing as long division, which means we look for remainders. So how many times does 3 go into 5? 1 time. So we know 5 divided by 3 is 1 point something. But with integer division or long division, this is 1 remainder 2. Right? 3 goes into 5 1 time. 3 times 1 is 3. It takes 2 more to get to the 5. That's a remainder of 2. Make sense? So how do we accomplish long division in our modern programming languages? Well, we use a slash for integer division, and we use usually a percent symbol for modulo, or the remainder. So in our modern languages, 5 divided by 3 would equal 1. 5 mod 3 would equal to 2. Make sense? All right, so that whole modulo thing, that remainder stuff, third grade math, pretty handy for us. Not just in number conversion stuff. Actually, almost all of our modern encryption algorithms are based on third grade math. It's pretty interesting with how powerful modulo can be. All right, so the way we're going to accomplish this, so we're going to take 63, and because we're going to base 2, we're going to divide that by 2. All right, so 63 divided by 2 is a 31. 31 times 2 is 62, and it takes 1 more to get to 63, so that's a remainder of 1. 31 divided by 2 is 15. 15 times 2 is 30, remainder 1. 15 divided by 2 is 7. 7 times 2 is 14, remainder 1. 7 divided by 2 is 3. 3 times 2 is 6, remainder 1. 3 divided by 2 is 1. 1 times 2 is 2, remainder 1. 1 divided by 2 is 0. 2 does not go into 1. 0 times 2 is 0 with remainder 1. I had to do something wrong here. So that's not 63. It shouldn't. Oh, it is 63. It is 63 because we got to go 1 more to get to the 64th place. Yeah, this is a really horrible example. Okay, the reason it's a horrible example is technically you read your answer from bottom up, but right now it's the same both ways. So I kind of picked a bad first number. We'll do a second one just to see. So this is 1, 1, 1, 1, 1, 1, 1. So that's 63 in binary. But we read it from bottom up. So let's pick a little bit of a different number here, just for whatever. Maybe 101. I think 101 will give us a little bit more mixture. All right, so 1001 divided by, or 101 divided by 2 is 50, remainder 1. 50 divided by 2 is 25, remainder 0. 25 divided by 2 is 12, remainder 1. 12 divided by 2 is 6, remainder 0. 6 divided by 2 is 3, remainder 0. 3 divided by 2 is 1, remainder 1. 1 divided by 2 is 0, remainder 1. Now, we know we're done when we finally get to the 0 here. That's our finish case. All right, so now our answer here, again, we read it from bottom up. So this is 1, 1, 0, 0, 1, 0, 1.
I have a different way that easy to remember decimal to binary.
Don't do a different way yet. I'm gonna show you guys some tricks once we get a little bit farther down. And I don't think it's gonna be easier to remember than this because we want to, just like before, we want to follow the identical patterns.
Well, the thing is mark something. It's just like make people confusing. I have the different way, like 100, 01 divided by 2 by 50, 25, 12, 6, 3, and 1. Every odd number is a 1 and even number is 0.
For the far right case, yeah. Oh, I get what you're saying. You're saying because of this guy, we know since he's odd, it's a 1. Since he's even, it's a 0.
Yes.
But you still need to get your next number.
Yeah, so you can divide it by 2 to get the next number. But whenever you divide it, the odd number is the 1.
Oh, I get it. But it's still the same thing. And that only works in binary where the same pattern is going to be for all the other bases too. But we're still doing the same thing because you still need to get this 25. You still need to get the 12. In binary, you only have a choice of 0 and 1. So it's you could almost flip a coin and be mostly right. Yeah. Okay. So that makes sense how that guy works?
Yeah.
All right. So let's now look at maybe 101 decimal to octal. So now instead of divide by 2, we're going to divide by 8. So 101 divided by 8 is 12. 12 times 8 is 96. So that's a remainder of 5. 12 divided by 8 is 1. 1 times 8 is 8 with a remainder of 4. Ruh-roh. 1 divided by 8 is 0. 0 times 8 is 0 with remainder 1. And we read it from bottom up. So this is 145 or 145 in octal. And now you can use your other way to go convert back to decimal and see that you'll get 101 out of that.
So if you want to convert from octal to hexadecimal, there's no shortcut, right? We have to go
Yeah, we'll talk about the shortcut. Yeah. Actually, there's not a shortcut for octal to hex. There's shortcuts for binary to octal and octal to binary and binary to hex and hex to binary. And we'll look at those. Although you could really go octal to hex shorter because you can kind of incorporate the binary trick in there and move pretty quickly. All right, and we'll see that. But it's not really a shortcut. It's just kind of convenient. All right, so now let's do a hex. And we'll do my favorite, 2989, decimal to hex. All right, so 2989 divided by 16. 2989 divided by 16 gives us a 186. 186 times 16 gives us a 2976, which is a remainder of 13. 186 divided by 16 is 11. That's a 176. So that's a remainder of 10. 11 divided by 16 is 0, so we know we're done. Remainder 11. Now we need to make sure we remember to convert these guys. So a D is, or 13 is a D, a 10 is an A, and 11 is a B. So then we read our answer from bottom up, B, A, D. That makes sense? What about decimal to decimal? Should also work. So 2989 decimal to decimal. We'll divide it by 10. That is 298. Remainder 9. Divided by 10 is 29. Remainder 8. Divided by 10 is 2. Remainder 9. Divided by 10 is 0. Remainder 2. Read your answer from bottom up. 2989. Make sense? All right, so it works for our patterns. All right, so now a big question might be, why use larger bases? What's the advantage of hexadecimal over something like binary? Okay, smaller footprint. We can represent big values. Because a value is a value regardless of what base we encode it in, right? Whether it's base 10 or base 2 or base 31, it's still the same underlying value. We're just representing it in a different base. So typically, well, what we would say is the higher the base, the smaller the footprint, right? Now, as computer science folk, though, we're kind of at a disadvantage here because our computers really like zeros and ones because of digital logic. That's their go-to move is zeros and ones. We kind of don't, right? We don't want that little 2-button keyboard. We're just tapping out zeros and ones left and right that we go insane. So now we need to look at, well, first of all, we all know that computers use hexadecimal values, right? It's a thing. We kind of recognize that there's hex values in computers. So the follow-up question would be why? Okay. I think you know the answer, so you're not allowed to answer. So why base 16 versus like base 20 or base 22? I mean, we probably chose a larger base because we needed to represent big numbers. Now, why do we need to represent big numbers? Like, what inside of a computer really needs representation? Really has a huge amount of numbers. We already talked about it a little bit today. Let's take our, who has the biggest hard drive in here? Anybody have a 1 terabyte drive? Anybody have bigger? Anybody have a 2 terabyte drive? Anybody have bigger 3 terabyte drive? Bigger than 3? All right, 3 terabytes. So we'll go with 3 terabytes. So we have a 3 terabyte drive. Now, did we talk about file systems last time? What's a file system? When I say file system, what am I talking about? Or if you want, give me some examples of file systems you've heard of, and I'll work backwards from there. What's your favorite file system? Okay, ext3, ext2. Let's not put that on there. Most people aren't going to have heard of that. While we stay in the Windows and Mac world. How many of you are Windows users in here? Okay, so you're all Windows users and nobody can tell me what the file system for Windows is? FAT's going to be one of the file systems we're going to put here. We're going to say FAT32. That's not Windows. It used to be Windows. What's Windows file system now? Did somebody actually say something, or was that just a fart?
NTFS.
NTFS. New technology file system. It's a Microsoft-based file system. What's the point of a file system? What's the job of a file system? Yeah, organizing your files, right? So it's the software that dictates when you store some data on a hard drive, how it gets stored, how it gets organized, how you're able to retrieve it without things getting broken, that kind of stuff, right? So it's important. It's something we use all the time. But as we just proved, we don't think about it, do we? It's a really important part of how our computer works. Yet we didn't even know what our file system of choice was. Now, what is kind of interesting here, though, is that he knew about Linux's journaling file systems, but didn't know about NTFS. You've heard of NTFS now that you heard it out loud, right? Yeah, ext2. ext2 is not journaling. ext3 is journaling. But that's Linux world. UFS or UTFS or some Unix file systems. But in any case, these are pieces of software that allow us to be able to store files on our computer. Now, kind of an interesting thing here. Let's see, what about jump drives? How many of you have a USB stick jump drive thing for storing stuff? Let's find out who has the biggest one of those. Who has at least an 8 gig? At least 16? At least 32? At least 64? At least 128? At least 256? Van, you still got 512? All right, so you got a 256. Okay, so Van has a 256 gigabyte solid state drive. I'm sorry, not solid state, USB drive, which technically is based on flash memory, so it is solid state, but whatever. Now, NTFS is going to be the file system that most Windows hard drives / solid state drives will be formatted. Now, when you buy a USB stick, a jump drive, what's the format on that? It's FAT32. Why? So you buy a USB stick from Amazon, shows up, you open it up, you slam it into your computer. The default's going to be FAT32. Not that you even notice, because we had some difficulty spitting these things out. But why is it FAT32? Believe me that it is.
Is it because there's not as very many pins, or essentially the data transfer?
No. Give you a little hint. NTFS is very proprietary. Microsoft made NTFS, and while they have, you can sort of, there's experimental support for NTFS on Linux, but it's pretty hit and miss. It's kind of dangerous. You wouldn't want to run Linux on an NTFS file system. Usually you're safe doing read-only on NTFS, but writing to NTFS, if you're not using something other than Windows, can be dangerous. We don't know. Microsoft has held the secret close to the chest. Let's just say that. Something along those lines. All right. Which probably means, so what are the top 2 computers that people are going to have out there today? Windows and Macs, right? Linux is going to be way down the line from there, but Windows and Macs. FAT32, even though it was a Windows file system early on, is known. So Macintosh computers understand FAT32. Linux understands FAT32. So if you take that jump drive and you plug it into any kind of computer, it'll work. No problem. Right? If you have a jump drive and it's formatted NTFS and you put it into a Mac, what's it going to do? It's going to ask you if you want to format this. I don't know how to use it. Make sense? All right. So does that mean FAT32 is always better to have on your USB stick? How many of you have a USB drive, but you only ever use it on a Windows machine? Well, many people. It's pretty common, right? Some people don't use Macs ever, or hardly ever. So does that mean you should convert yours to NTFS? Or is it no big deal? Why don't you just leave it as FAT32? That way you at least have the option. How many of you have ever tried to store, so let's, you have at least an 8 gigabyte jump drive. How many of you ever tried to store a single 5 gigabyte file on that jump drive? Or larger than 5 gigabytes, but smaller than 8 gigabytes? Anybody ever tried to put a really large file like that onto a jump drive?
Window machine, the window OS.
Okay, like the ISO for Windows 0, and it was at least bigger than 4 gigs.
Yeah.
Okay, what happens? What does it say when it tries to store it on your jump drive?
You have to restore it by an NTFS.
Okay, so the error message you get is not enough space, out of memory. So even if Van is sitting there with this 256 gigabyte jump drive, and let's say that he had 250 gigabytes free, and he tries to put this measly 5 gigabyte file on there, which he has plenty of space for, it'll tell him he's out of space. Yeah, FAT32, its limitation is the maximum size of a single file is 4 gigabytes. 4096. That's an unsigned 32-bit value. 2 to the 32nd power in bits. Make sense?
So wait, 32 is the base? Is that what you're saying?
Yeah, so I mean, in this particular case, FAT32 is based on, it's not that it's base 32. The 32 in FAT32 happens to represent the number of bits that they use to what's called index that file system. And that'll make sense to you in a second when I talk about this 3 terabyte thing. But in any case, because it's a 32-bit file system, the largest single file that it can address, that it can keep track of all the little pieces of, is 4 gigabytes. Anything bigger than 4 gigabytes, it doesn't have enough individual numbers to keep track of all the little spots. And we'll talk about that at the 3 terabyte level because that's the scarier example, so it kind of exaggerates it. But you have that limitation with FAT32. Back when you had FAT16 as the standard file system, this kind of goes back when we were a little bit ago when we were talking about cost of memory and stuff like that. So, I mean, what's the smallest hard drive that any of you remember? It's the smallest hard drive you've ever owned. Actual hard drive that goes in the computer, not jump drives and stuff, but 4 gigabyte? Okay, anybody remember a smaller hard drive than 4 gigabyte? It's like 4 gigabyte. Isn't that just a shoe? Windows 99? There was no Windows 99. There was a Windows 98. Yeah, so that computer, that 1996 computer that I had 8 megabytes of memory in, how much hard drive space do you think that came with? 420 megabytes. 420 megabyte hard drive. So let's say when we started, let's say you had a 4 gigabyte drive. 4 gigabytes are good for this example. And you were running you were running Windows 95. So the first version of Windows 95 actually was based on the FAT16 file system. So it's a 16-bit file system. You could put a 4 gigabyte hard drive into your computer, but you could not create a single volume that was 4 gigabytes. You had to create 2 partitions on that drive, each one being 2.1. Well, you'd have 2.1 and 1.9 gigabytes, because the largest single partition you could have with FAT16 was 2.1 gigabytes. Make sense? So it's interesting. We used to have limitations like that. And we still sort of kind of see those today when you try to put a really large file on a FAT32 jump drive. But generally speaking, I mean, you could reformat your jump drive to NTFS in 2 seconds and you can hold, I think the maximum size is 16 terabytes or something like that for NTFS, but I might be wrong. It's way bigger than 5 gigabytes. It's not going to be a problem for you for a while. But in any case, reformatting it takes 2 seconds. You're going to lose all the data that was on there, and then when you take it over to a Mac, it's not going to be able to read it. You might not care. Go ahead.
What is it, Max hard drive?
HFS, which is a Unix-based
Unix-based.
file system. It can hold big files too. Just HFS, NTFS, they don't. Yeah, they don't talk. Okay, so the real example here for us, we kind of talked about why do we need big numbers? Why do we need big bases for storing stuff in our computers? So if we think about the 3 terabyte hard drive, all right, we can create a single 3 terabyte partition with our modern file systems, right? No problem. Typically, when we talk about file systems, and we're not going to go too far into that in here because that's more of an operating systems concept, but I'm going to talk about the high level because all these, something that Dr. Locklear talks a lot about is this idea of the grand ideas of computer science. All right, so if you haven't had him, has everybody in here, well, you've never had him for a class, but has everybody else in here had him for a class? Dr. Locklear? So that's something he always comes back to, right? It was actually his research area, is this grand ideas of computer science. And it really makes a lot of sense because the idea is that no matter what class you're in, you hear the same material but from a little different angle. Because all the areas of computer science are interrelated. Just different edges touch each other. Kind of make sense? So we're talking about an operating system concept in here, but we're talking about it from the lens of the underlying architecture, as opposed to the lens of the operating system software, even though they're related. Make sense? So we're not going to focus on the software side of things, but we want to focus on how computers work and why they work the way they work, and why some of these decisions were made. So if we deal with a 3 terabyte hard drive, and it's using some sort of reasonable file system, unimportant what the actual file system is, we typically break file systems down into blocks. Okay, so if you want to think about your 3 terabyte hard drive, the way it works in actuality, think of it as like a really, 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 really long street. Okay, so in real life, we have houses that are in these, we have neighborhoods and cities and stuff like that. Each house has an address, right? And addresses are made up of, you have a street address, you have a number, then you have the street, and, we can even take it further than that. Sometimes, especially you go to Cedarburg, you get some really weird addresses up there. Have you seen the Cedarburg addresses? It's like NS32, County W. They have it's really cryptic. You can't even put it in Google Maps. It's stupid. But in any case, have you seen them? Yeah, Cedarburg addresses are just ridiculous, and there's other places that use it. But in any case, it's the same kind. Yeah, so in any case, we think about houses, the location of a house in real life, with an address. Okay, but we kind of need a little bit more complex addresses because we don't have one big long straight road. Like, we kind of need to know what city the place is in. We need city, we need state, you need street, and you need the house number. And then you can get to most places unless the roads don't go there, right? Now, the funny thing is that most, even technical people, before they learn the underlying stuff, think that memory in computers is harder. It's like, oh, addresses in real life is easy. No, our real life addressing stuff is way more complicated than computers. Computers just say, look, everybody lives on the same street. Same state, they're on this street. The real question is how far down that street is the house you're looking for. All right, so we call them blocks. So each house, if you will, is one block away from it. Not a block like we think of. So a modern file system, we'll just pick a number out of this guy, might use a 4 kilobyte block size. Let's use that as an example. Okay, 4 kilobyte block size. Now, what does that mean? That means the smallest piece of information that can be stored on a hard drive is 4 kilobytes. Okay, 4 kilobytes, smallest piece of information. That means that we could have some wasted space. If you need to store 9 kilobytes on a hard drive, what are you going to do? You're going to fill one block up, you're going to fill another block up, and then you're only going to fill 25% of the third block up. So you're going to waste 3 kilobytes for that data. But being wasteful is bad, right? Well, back in 1968. But Van over here has a 3 terabyte hard drive. He's not going to miss those 3K. Life goes on, right? So the most we can waste is 3.99K, right? Depending how far down you go. So the 1 bit short of 4K. That's the most space that we can waste on a per storage basis. Then you can have that on multiple files that are stored, so you have waste that grows. But if we go way back to the beginning, when we wouldn't want to be very wasteful, we might decide that we want our block size to be a bit. We'll talk about why that's kind of a bad idea. We'll just operate off kilobytes here for a second. So we're going to have a 4 kilobyte block size. So if we want to think about it, kind of with that street example, we have a big long street and every single house is 4 kilobytes. Okay? So we want to know how many of those blocks, how many of those houses exist in 3 terabytes. So let's get terabytes into kilobytes. So 3 times 1024 is gigabytes, times 1024 is kilobytes, right? Then we're going to divide that by 4. So 3 terabytes times 1024 is gigabytes, times 1024 is, megabytes, sorry, times 1024 is kilobytes, divided by 4. This is the number, who's going to let me copy this guy? There we go. Almost, there we go. This is the number of unique houses on our really long street. Make sense? And these guys are indexed from 0 to 805,306,367. Make sense? That's how they're indexed. So if somebody says, oh yeah, come over for dinner, I'm in house 107,201,008. Don't make me repeat that. I'm down the street. Okay? Just go. You want to go down there. That's kind of a scary type of number for us to think of in counting, right? And keep in mind that that's base 10. The reality is if we were to convert that to binary, which computers like, that is like ridiculous, right? Just a whole bunch of zeros and ones. Let's even see if we can get a website that'll convert. We can obviously convert it ourselves, but that might take a bit. So let's do that number decimal to binary. Let's see if we have a site that will. It's in decimal. We want to go to binary. Oh, actually, it's not bad because of the number of zeros. So remember, this is the ones place, 2s, 4s, 8s, 16s, 32, 64, 128, 256, 512, blah, 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 millions. Perfect. And then all the little buckets in the middle, right? So we use all of these bits to represent an individual address. So is this 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. 30 bits. So we need 30 bits to uniquely represent every single house on that big long street. Computers are fine with that. We only need a 32-bit register to hold that, right? No problem. 32 bits, it was non-issue. We don't like that. We start getting a little frustrated when we get bigger than 4 bits. But at the same time, we don't really like that number either. I mean, we're really pretty picky when you think about people. Like we have our comfort zone, and everything in that is kind of okay. So at the same time, we look at this number and say, you know what? That number is actually even pretty big for a decimal number in terms of footprint. How much space it takes. So if we go back into this thing, I'm going to take this guy and let's convert him to hexadecimal. Sarah, do I get another? Is there a button to click?
That's the Pac-Man button.
Yeah, I need my Pac-Man button. There we go. So that's the hexadecimal version of that guy. So that's what, 1, 2, 3, 4, 5, 6, 7, 8, as opposed to 9. Saved a little bit smaller footprint. But that's only for the far, far, far down addresses, right? We really have smaller numbers and we get shorter than that. But as we go to higher bases, we get smaller footprints for holding the same value, for encoding the same value. That make sense? So this is where when we index memory, whether it's a hard drive or system RAM or a cache, I mean, cache memory is usually fairly small. Maybe it's 1 megabyte or 3 megabytes or something like that. Hardware registers are 8 bits, 16 bits, 32 bits, 64 bits, things like that. So they're really small. We don't really need something that special to index them. But as we get to our bigger size memory, so typically system RAM and your hard drives, obviously, which have a lot of space on them, and we need to index them. We need to keep track of house 0, house 1, house 2, house 3. There's a lot of houses. So we need some sort of numbering system that allows us to conveniently keep track of all the houses. Conveniently talk about house 4 zillion. Make sense? But at the end of the day, our computers still want to work in binary. That's their go-to move. That's their bread and butter. They want binary numbers. So we need to have the ability to move between. So getting back to the question I asked earlier, why hex? Why not base 30? Wouldn't 30 give us an even smaller number? Yeah, so this really means, so base 16 uniquely, as far as a higher base, uniquely can be represented in binary through a trick. Okay, and let's look at some of these things. So are we all pretty comfortable with converting numbers now? All right, so I'm gonna give you, we're gonna do another little test thing here. So I'm gonna say, all right, so you have to convert 1011110101 from binary to hex. If you know the trick, you're not allowed to use the trick. Using only the stuff I taught you today, convert that binary number to that hexadecimal number, which means you're going to have to do 2 steps, right? Binary to decimal, then decimal to hex. All right, so let me pause this recording. Go ahead and do that. So we got it. So let's go ahead and solve this guy. So we first need to take this guy from binary to decimal. So we have a 1 times a 1. Oh, here, I'm actually going to just do a little shorthand. So this is a 1 plus, not a 2, plus a 4, plus a 16, a 32, a 64. 16, 32, 64, plus a 256. $373. So that's 373 in decimal, right? And you see how I did this. So, this is 1 times 1 is 1, plus 0 times 2 is 0, plus 1 times 4 is 4. So I just did a little bit of the math in the middle. All right, so now we need to convert 373 from decimal into hex. So we're going to divide that by 16. 373 divided by 16 gives you 23. 23 times 16 is 368, so that's remainder 5. 23 divided by 16 is 1, remainder 7. 16 divided by 1 is 0 with remainder 1. We read it from bottom up, so this is the hexadecimal number 175. We don't need to convert any of them to letters because they're all 0 through 9. Make sense? Now, the shortcut here is that, remind me, what's the legal alphabet for hexadecimal? 0 to 9 and then A through F, because the legal digits are 0 to 15, right? For base 16. 0 to the base minus 1, so 0 to 15. How do you write a 15 in binary? 1, 1, 1, 1. So the largest hexadecimal number can be represented in 4 bits. Do you know what do you know what the name for 4 bits is in computer science? It's not an 8 bits is a byte. What's 4 bits? It's not used real often, but sometimes you'll see it in a book. It's called a nibble. N-I-B-B-L-E. Nibble. All right. So what I'm going to do here is I'm going to take our number. Oh, that's a big number there. Just type it again. 1011101001. And I'm going to break this guy into 4-bit chunks. Now, if it makes you feel better, you can go ahead and pad the beginning with some extra zeros to give you a full 4 bits here. But having extra zeros out front doesn't change the value, right? This first nibble is a 1. The second nibble is a 7. The third nibble is a 5. This is 1 in the ones place plus 1 in the fours place. That's a 5. 1 in the ones place plus 1 in the twos place plus 1 in the fours place is a 7. Plus 1 in the ones place is a 1. 175. We were able to go from binary to hex real quick. Make sense? The same thing is true if we have whatever that number is, and we want to convert that to octal. What's the range of values that go into octal? It's a base 8, so it's 0 to 7. How many bits does it take to represent a 7? What's the value? How do you write 7 in binary? 111. 3 bits. So we're going to take this value, 101101011010. We're going to break it into little 3-bit chunks. This is a 2. This is well, I'll put a little space. That's a 6. This is a 1 in the ones place, 1 in the fours place. So that's a 5. And that's a 2. So 2652 is the octal value of this binary number. See how that works? This is the binary number 2. This is the binary number 5. This is the binary number 6, 4 plus 2. This is the binary number 2. We broke it up into 3-bit groupings because octal is represented in 3 bits. A 0 is 000, a 7 is 111. Just like hexadecimal, a 0 is 0000, and an F or a 15 is 1111. Make sense? All right, so we like the little shortcut stuff. So that kind of answers the question, why do we use octal and hexadecimal on PCs? It's because we need that convenience of moving between some different bases for various reasons. and those bases happen to be very compatible with binary. Make sense? What is 11111? What's that in binary? This is the ones place, 2s, 4s, 8s, 16s. So that's 24 plus 4 is 28, 31. So this is 32 bits, base 32, right? 0 to 31 is base 32. So to take us to the next level, to have the next convenience. So if I said, if you want to really impress people, I guess, we take this value, we take this guy, and I say convert this guy from binary to base 32. We would do chunks of 5. So this is a 1. This is a 1s, 2s, 4s, 8s. This is 12, 13. That's a 13. This is the 2s plus 8. This is a 10. So that is 1DA. Base 32 seems ridiculous, and we don't binary to 32, no problem. So that means that as soon as we start getting out of control, right? When 3 terabytes, when we go up to way more than that, either to petabytes or exabytes, whatever it is, where that base 16 the hex isn't gonna cut it anymore. We do have another step we can take. And then what do you think the next guy is? The next guy would be 64, 128. So we can just keep making those jumps. Make sense? So hexadecimal is cool, but hexadecimal has been cool for a while. So it's almost not cool anymore. Pretty soon it won't be. All right, let's take just a real quick break. Let's take 5 minutes, get up, stretch, whatever. Then I want to come back and I want to start prepping our Android application for our homework assignment so I can give you a good starting point.